In 2021, a monumental moment in the history of space exploration unfolded as NASA successfully launched the James Webb Space Telescope into the vast expanse of the universe. This groundbreaking endeavor came to fruition through the collaborative efforts of individuals from countless countries spanning 3 decades. Fortunately, James Webb, truly living up to its billing, has been a game-changer in cosmology ever since it began its journey. You can marvel at the breathtaking images that it has gifted us, pushing the boundaries of scientific discovery. James Webb, with its unrivaled capabilities, has opened our eyes to the cosmos. From studying the atmospheres of nearby exoplanets to uncovering the secrets of the early universe, the Webb Telescope has never disappointed us. It has taken amazing pictures of the cosmos, but also led to discoveries that, while breathtaking, but threaten to upend the standard model of cosmology. Stunning discoveries made by James Webb have shown that the universe before the first stars and galaxies formed is beyond our understanding, and the discovery of nothingness could be the end of our current cosmological models. Join us as we dig deep into James Webb's astonishing discoveries about the early universe. Of all the questions humanity has ever pondered, perhaps the most profound is, where did all of this come from? For generations, we told one another tales of our own invention and chose the narrative that sounded best to us. The idea that we could find the answers by examining the universe itself was foreign until recently, when scientific measurements began to solve the puzzles that had stymied philosophers, theologians, and thinkers alike. The 20th century brought us general relativity, quantum physics, and the Big Bang, all accompanied by spectacular observational and experimental successes. These frameworks enabled us to make theoretical predictions that we then went out and tested, and they passed with flying colors while the alternatives fell away. But, at least for the Big Bang, it left some unexplained problems that required us to go farther. When we did, we found an uncomfortable conclusion that we're still reckoning with today. Any information about the beginning of the universe is no longer contained within our observable cosmos. Here's the disconcerting story. In the 1920s, just under a century ago, our conception of the universe changed forever, as 2 sets of observations came together in perfect harmony. For the past few years, scientists led by Vesto Slipher had begun to measure spectral lines, emission, and absorption features of a variety of stars and nebulae. Because atoms are the same everywhere in the universe, the electrons within them make the same transitions. They have the same absorption and emission spectra. But a few of these nebulae, the spirals and ellipticals in particular, had extremely large redshifts that corresponded to high recession speeds, faster than anything else in our galaxy. Starting in 1923, Edwin Hubble and Milton Humason began measuring individual stars in these nebulae, determining the distances to them. They were far beyond our own Milky Way, millions of light-years away in most instances. When you combine the distance and redshift measurements together, it all pointed to one inescapable conclusion that was also theoretically supported by Einstein's general theory of relativity. The universe was expanding. The farther away a galaxy is, the faster it appears to recede from us. If the universe is expanding today, that means that all of the following must be true. The universe is getting less dense as the fixed amount of matter in it occupies larger and larger volumes. The universe is cooling as the light within it gets stretched to longer wavelengths, and galaxies that aren't gravitationally bound together are getting farther apart over time. Those are some remarkable and mind-bending facts as they enable us to extrapolate what's going to happen to the universe as time marches inexorably forward. But the same laws of physics that tell us what's going to happen in the future can also tell us what happened in the past, and the universe itself is no exception. If the universe is expanding, cooling, and getting less dense today, that means it was smaller, hotter, and denser in the distant past. The big idea of the Big Bang was to extrapolate this back as far as possible, to ever hotter, denser, and more uniform states as we go earlier and earlier. This led to a series of remarkable predictions, including that more distant galaxies should be smaller, more numerous, lower in mass, and richer in hot blue stars than their modern-day counterparts. There should be fewer and fewer heavy elements as we look backward in time. There should come a time when the universe was too hot to form neutral atoms, and a leftover bath of now cold radiation that exists from that time. There should even come a time where atomic nuclei were blasted apart by the ultra-energetic radiation, leaving a relic mix of hydrogen and helium isotopes. All four of these predictions have been observationally confirmed, with that leftover bath of radiation, originally known as the primeval fireball, and now called the cosmic microwave background. Discovered in the mid-1960s, often referred to as the smoking gun of the Big Bang. You might think this means that we can extrapolate the Big Bang all the way back, arbitrarily far into the past, until all the matter and energy in the universe is concentrated into a single point. The universe would reach infinitely high temperatures and densities, creating a physical condition known as a singularity, where the laws of physics as we know them give predictions that no longer make sense and cannot be valid anymore. At last, after millennia of searching, we had it, an origin for the universe. The universe began with a Big Bang some finite time ago, corresponding to the birth of space and time, and that everything we've ever observed has been a product of that aftermath. For the first time, we had a scientific answer that truly indicated not only that the universe had a beginning, but when that beginning occurred. In the words of Georges Lemaitre, the first person to put together the physics of the expanding universe, it was a day without yesterday. However, we all know that something is awry in our expanding cosmos. There were a number of unresolved puzzles that the Big Bang posed, but presented no answers for. And with the arrival of James Webb, the world's most powerful telescope, alarming holes have been growing in this picture. The shocking discoveries of the James Webb Telescope have created a stir in the field of astronomy. Among all the discoveries made by the Webb Telescope so far, the most surprising discoveries are from the early universe. We've already seen how these early galaxies display completely different properties than scientists expected. When the Super-Me Observatory opened its lens, extremely distant yet very bright galaxies immediately shone into the telescope's field of view. They were just so stupidly bright, and they just stood out, said Rohan Naidu, an astronomer at the Massachusetts Institute of Technology. The galaxies' apparent distances from Earth suggested that they formed much earlier in the history of the universe than anyone anticipated. Doubts swirled, but in December, astronomers confirmed that some of the galaxies are indeed as distant and therefore as primordial as they seem. The earliest of those confirmed galaxies shed its light 330 million years after the Big Bang, making it the new record holder for the earliest known structure in the universe. That galaxy was rather dim, but other candidates, loosely pegged to the same time period, were already shining bright, meaning they were potentially humongous. How could stars ignite inside superheated clouds of gas so soon after the Big Bang? How could they hastily weave themselves into such huge, gravitationally bound structures? Finding such big, bright, early galaxies seems akin to finding a fossilized rabbit in Precambrian strata. That's why scientists named these impossible early galaxies universe breakers. Astronomers began asking whether the profusion of early big things defies the current understanding of the cosmos. Some researchers and media outlets claimed that the telescope's observations were breaking the standard model of cosmology, a well-tested set of equations called the lambda cold dark matter, or the mathematical model of the Big Bang theory, thrillingly pointing to new cosmic ingredients or governing laws. It has since become clear, however, that the lambda cold dark matter model is resilient. Instead of forcing researchers to rewrite the rules of cosmology, James Webb's findings have astronomers rethinking how galaxies are made, especially in the cosmic beginning. The telescope has not yet broken cosmology, but that doesn't mean the case of the two early galaxies will turn out to be anything but epical. But the latest discoveries of the Webb Telescope have once again created havoc in astronomy. In addition to early galaxies, Webb discovered an early black hole that may be older than our universe. How could a thing be older than the universe? Or, conversely, how could the universe be younger? Obviously, the appearance of hundreds of black holes and galaxies that shouldn't exist had turned them on to the question of our cosmic origin. However, note that no matter how advanced our telescopes are, we will never see the first moment of our universe. Because the first moment of our universe is so complex that our physics, such as gravity, quantum mechanics, nuclear physics, and classical physics, will all collapse at this stage. In other words, any information about the beginning of the universe is no longer contained within our observable cosmos. With incomplete observations, we cannot say that our universe had a beginning. There is a unique possibility that in the beginning there was no beginning. Perhaps our universe has always existed, and a theory of quantum gravity reveals how that could work. As Bruno Bento, a physicist who studies the nature of time at the University of Liverpool in the UK, said, "Reality has so many things that most people would associate with science fiction or even fantasy." In his work, he employed a new theory of quantum gravity called causal set theory, in which space and time are broken down into discrete chunks of space-time. At some level, there's a fundamental unit of space-time according to this theory. Bento and his collaborators used this causal set approach to explore the beginning of the universe. They found that it's possible that the universe had no beginning, that it has always existed into the infinite past and only recently evolved into what we call the Big Bang. Quantum gravity is perhaps the most frustrating problem facing modern physics. We have two extraordinarily effective theories of the universe: quantum physics and general relativity. Quantum physics has produced a successful description of three of the four fundamental forces of nature, including electromagnetism, the weak force, and the strong force down to microscopic scales. General relativity, on the other hand, is the most powerful and complete description of gravity ever devised. But for all its strengths, general relativity is incomplete. In at least two specific places in the universe, the math of general relativity simply breaks down, failing to produce reliable results, in the centers of black holes and at the beginning of the universe. These regions are called singularities, which are spots in space-time where our current laws of physics crumble, and they are mathematical warning signs that the theory of general relativity is tripping over itself. Within both of these singularities, gravity becomes incredibly strong at very tiny length scales. As such, to solve the mysteries of the singularities, physicists need a microscopic description of strong gravity, also called a quantum theory of gravity. There are lots of contenders out there, including string theory and loop quantum gravity. And there's another approach that completely rewrites our understanding of space and time. In all current theories of physics, space and time are continuous. They form a smooth fabric that underlies all of reality. In such a continuous space-time, 2 points can be as close to each other in space as possible, and 2 events can occur as close in time to each other as possible. But another approach, called causal set theory, reimagines space-time as a series of discrete chunks, or space-time atoms. This theory would place strict limits on how close events can be in space and time, since they can't be any closer than the size of the atom. For instance, if you're looking at your screen reading this, everything seems smooth and continuous. But if you were to look at the same screen through a magnifying glass, you might see the pixels that divide up the space, and you'd find that it's impossible to bring two images on your screen closer than a single pixel. This theory of physics excited Bento. He said, "I was thrilled to find this theory, which not only tries to go as fundamental as possible, being an approach to quantum gravity and actually rethinking the notion of space-time itself, but which also gives a central role to time and what it physically means for time to pass, how physical your past really is, and whether the future exists already or not." Causal set theory has important implications for the nature of time. According to Bento, a huge part of the causal set philosophy is that the passage of time is something physical, that it should not be attributed to some emergent sort of illusion, or to something that happens inside our brains that makes us think time passes. This passing is, in itself, a manifestation of the physical theory. So, in causal set theory, a causal set will grow one atom at a time and get bigger and bigger. The causal set approach neatly removes the problem of the Big Bang singularity because, in the theory, singularities can't exist. It's impossible for matter to compress down to infinitely tiny points. They can get no smaller than the size of a space-time atom. So without a Big Bang singularity, what does the beginning of our universe look like? That's where Bento and his collaborator, Stav Zalel, a graduate student at Imperial College London, picked up the thread, exploring what causal set theory has to say about the initial moments of the universe. Their work appears in a paper published to the preprint database Arxiv. The paper examined whether a beginning must exist in the causal set approach. In the original causal set, formulation and dynamics, classically speaking, a causal set grows from nothing into the universe we see today. In our work instead, there would be no Big Bang as a beginning, as the causal set would be infinite to the past. And so, there's always something before. Their work implies that the universe may have had no beginning, that it has simply always existed. What we perceive as the Big Bang may have been just a particular moment in the evolution of this always existing causal set, not a true beginning. There's still a lot of work to be done, however. It's not clear yet if this no-beginning causal approach can allow for physical theories that we can work with to describe the complex evolution of the universe during the Big Bang. As Bento concluded, one can still ask whether this causal set approach can be interpreted in a reasonable way or what such dynamics physically means in a broader sense. But we showed that a framework is indeed possible. So at least mathematically, this can be done. In other words, it's a beginning. After all, we have to accept that we have no way of knowing how, or even if, the universe started. The total amount of information accessible to us in the universe is finite, and hence, so is the amount of knowledge we can gain about it. There's a limit to the amount of energy we can access, the particles we can observe, and the measurements we can make. That doesn't mean we're done, or that we shouldn't strive to learn everything we absolutely can. Only we can push the frontiers of knowledge back as far as they can go. There's a whole lot left to learn and a whole lot that science has yet to reveal. If we continue to look, many of the present unknowns will likely fall in the near future. But what is knowable is finite, and this implies that there are necessarily some things we may never know. The universe may yet be infinite, but our knowledge of it never will be. Regardless, one thing can't deny, we're living in the golden age of cosmology. Recent years have brought a flood of extraordinary findings. We've found ironclad evidence for black holes, cataloged more than 5,500 planets orbiting stars near us in the Milky Way, explored the Pluto system robotically. We've got a good understanding of the age, size, evolutionary history, and fate of the universe. We know what will eventually happen to life on Earth. The big questions have largely fallen into place with answers, or at least partial answers. And we knew almost nothing of those answers, say 50 years ago. In other words, astronomy has elevated our knowledge such that we know that we live in a vast galaxy inside a vast universe, and that we're literally made of atoms from the stars. Don't worry. Be happy. You're interested in astronomy and immersed in a golden age of discovery like we've never seen before. A remarkable information, a new space telescope set to launch in January 2024 will look at the cosmos with a revolutionary lobster eye, hunting for X-ray bursts that stem from some of the universe's most powerful phenomena, including feeding black holes, colliding neutron stars, and exploding stars. Named for none other than Albert Einstein, the Einstein probe is a joint effort between the European Space Agency, the Max Planck Institute for Extraterrestrial Physics, and the Chinese Academy of Sciences. This spacecraft will possess highly sensitive, next-generation X-ray instruments and exhibit an exceptionally wide field of view, allowing scientists to both pinpoint new events and study them in detail. As Eric Kolkers, ESA's Einstein Probe project scientist, said, "The cosmos is our only laboratory to investigate the most energetic processes. Missions like Einstein Probe are essential to advance our understanding of these processes and to learn more about fundamental aspects of high-energy physics. X-rays are emitted by powerful and violent events like supernovas, from which they're launched as the cores of dying stars collapse. They're directly connected to stellar material that is shredded before it gets consumed by black holes too, as well as to the collisions of ultra-dense, already dead stars called neutron stars. Because these violent cosmic events are often short-lived, however, the X-ray light they emit can be highly variable and unpredictable. This light can appear and disappear and brighten and dim incredibly rapidly, often appearing in the sky for only a brief moment before vanishing for long periods. If they reappear at all, that is. Spotting these X-rays is highly desirable for scientists because encoded within this high-energy light is information about the source that produced it. That means by observing X-rays, the Einstein probe could help scientists decode such events while simultaneously enabling astronomers to pinpoint new X-ray sources. Because neutron star collisions emits both X-rays and gravitational waves, first predicted by Einstein in his 1915 theory of gravity general relativity, the Einstein probe could help gravitational wave detectors locate the source of these tiny ripples in space-time that have traveled across millions or even billions of light years. This could ultimately help scientists observe these collisions before they fade, revealing more about the dynamics of these collision events and the unique physics that occur around them. For instance, heavy elements such as gold are known to be created in the aftermath of neutron star collisions. To achieve its pioneering view of the universe, the Einstein probe is equipped with two revolutionary instruments, the Wide Field X-ray Telescope, or WXT, and the Highly Sensitive Follow-up X-ray Telescope, or FXT for short. The WXT gets its expanded view of the cosmos from its unique modular design, which resembles the eye of a lobster. Lobster eyes, unlike other animal eyes, have evolved to perceive light via reflection rather than refraction, meaning these crustaceans have a remarkable 180-degree field of view. The so-called micropore optics technology of WXT allows the Einstein probe to see 3,600 square degrees, which encapsulates 10% of the entire celestial sphere over Earth in just one image. This enables it to see nearly the entire night sky over Earth in just 3 orbits around the planet, each of which would take the Einstein probe just around 96 minutes to complete. Once an interesting or new X-ray emitting event is spotted by WXT, the Einstein probe's FXT instrument will take over, targeting the X-ray source and studying it in much greater detail. In addition to this, when WXT makes a notable X-ray detection, the Einstein probe will fire a signal to ground-based observatories, allowing them to train other telescopes on the source and study it in a range of other light frequencies, ranging from low-energy long-wave radio waves to high-energy shortwave gamma rays. This multi-wavelength data could be absolutely vital in conducting detailed investigations of supernovas, neutron star collisions, and feeding black holes. In short, thanks to its innovative design, Einstein probe can monitor large swaths of the sky at a glance. In this way, we can discover many new sources while at the same time studying the behavior of X-ray light coming from known celestial objects over long periods. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.